Running every eval case is expensive, but random samples miss the failures that matter. We'll build targeted sampling in Python to catch regressions with fewer tests. This is the pattern you'll be able to implement by the end, which prioritizes regression cases and trims evaluation volume. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Evaluating large language models often means running hundreds of prompts whenever you tweak a model. That eats time and budget and slows down rollouts. The goal is to catch real regressions before users do, while running far fewer checks. This fits into monitoring and CI, where fast, focused feedback matters more than exhaustive reports. The idea is straightforward. Keep a small catalog of representative prompts, each labeled by difficulty. Keep a healthy baseline run. When a new model appears, look for prompts that dropped in score. Prioritize those drops, and always include one hard guard case. That focuses compute on likely failures while still exercising a tough challenge. We will build a tiny catalog, record a baseline, simulate a new run, compute drop-driven risk scores, and pick a targeted batch that catches regressions but saves time. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a small, reproducible prompt catalog, so we can reason about tiers and coverage before we trim anything. This snippet builds a deterministic mini catalog of LLM eval prompts with tier labels. The fixed random seed sets up reproducible sampling later. We store a concise list of dicts, called test cases, that hold IDs plus theme and tier metadata, so you can see coverage at a glance. Assorted comprehension pulls the unique tiers into tiers, which lets us measure tier mix when we reduce the suite. Finally, we print the catalog and the tier distribution to confirm we begin with 4 prompts spanning easy, medium, and hard, preserving the baseline coverage we need. Now that we have the catalog, we need a baseline to compare future runs against. Record the healthy numbers first. This example records baseline evaluation quality, so we know what a healthy run looks like. The dict baseline run maps each prompt ID to a tuple of score and latency taken from our last reliable model run. We compute means for score and latency to get a simple summary metric for comparisons later. Because the tuples line up with the IDs from the catalog, we can compute deltas later without reshaping data. Printing the baseline score and average latency reminds us the reference run scored 0.92 with a 2.53 second average, which is the threshold we want to preserve. With a baseline, we can simulate a new model and ask how often random sampling would find regressions. That shows the risk of naive monitoring. This snippet compares full pair coverage to reveal how often naive random sampling would hit current regressions. Candidate run carries the new model's scores and latencies keyed by the same IDs, so we can subtract baseline run and isolate score drops. We mark any drop over 0.05 as a regression and collect those IDs into regression set. Then we use itertools.combinations to enumerate every 2K sample and count how many pairs touch the regression set, dividing by the 6 possible pairs to get a random hit rate. The printed hit rate and regression list show that random 2-case pulls catch the 2 regressions only 83% of the time, which is risky for critical monitoring. Random 2-case samples miss failures too often, so we need a smarter shortlist that biases toward recent drops while still testing a difficult prompt. This snippet builds a smarter shortlist by scoring prompts with observed drops and a difficulty-aware guard. Drop scores keeps only positive deltas so random improvements don't inflate risk. And sorted top drop surfaces the two worst offenders. Remaining filters the catalog to everything else. And we use a max over tier weight to pick the highest tier guard case so we don't ignore hard but currently stable prompts. The targeted batch then concatenates the worst drops with that guard, letting us watch likely regressions while still exercising a demanding challenge. The printed targeted batch shows law edge, safe prompt, and math hard, demonstrating the heuristic zeroes in on risky cases without dropping the toughest math check. Finally, we run the targeted picks and measure how much we caught and how much time we saved compared to the full suite. This example measures how effective the targeted batch is once we actually run it. Found filters the targeted batch by the same 0.05 drop rule, so only meaningful regressions remain. We sum candidate run latencies for the whole suite and for the targeted picks to compute execution time saved. Coverage ratio divides the targeted size by the total catalog length so we can quantify the reduction. The printed caught list, latency saved, and coverage ratio confirm we detected both regressions while running only 75% of the prompts and reclaimed 1.70 seconds of budget. If you map this toy to a real pipeline, the catalog becomes a curated set of a few dozen prompts, and the latency sums move from single seconds to minutes. The principle is the same. Prioritize observed drops and keep a hard guard. Recap. This is a drop-driven sampling pattern. Prioritize prompts that recently declined in score, and always include a hard guard case. Use it in monitoring and CI when you need fast, budget-aware regression detection. One caveat: if your catalog is too small or not representative, you can steer detection toward a narrow failure mode. Next step, scale the same approach by swapping the distance metric or feature you use to score risk. For example, try a semantic similarity feature for clustering prompts before scoring drops. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.